Our universe's age has been a subject of intense interest and debate among scientists for centuries. At first, it appeared to be a straightforward question, but the quest for an answer has proven to be far more complex than anticipated. Even today, this question continues to spark debate, as new research frequently challenges our current understanding of the universe's age and its countless galaxies. Just a week ago, a groundbreaking study based on data from the James Webb Space Telescope introduced a bold challenge to the long-standing consensus that the universe is approximately 13.8 billion years old. This new research suggests the universe could be twice as old as previously thought, potentially overturning the current cosmological model and offering solutions to long-standing mysteries surrounding the first galaxies. But is this truly feasible? Let us explore this theory as we dive into the vastness of the cosmos and analyze this fascinating discovery. If you're keen on staying updated with the most recent information from space and beyond, don't forget to subscribe to our channel, like this video, share it to spread the word, and activate the notification bell. It is essential to recognize that one of the most insightful facts we know about the universe is its age: 13.8 billion years. However, this figure is now being reassessed due to a recent surge of exciting new research. By traveling back in time, we will eventually learn that the early universe was vastly different from what we observe today. The stars and galaxies we see now formed through the gravitational merging of objects that consisted of younger, more pristine stars. In the very early moments of the universe, neither stars nor galaxies existed. If we continue to look backward, we eventually reach the Big Bang, which marks the origin of the universe as we understand it today. Currently, astrophysicists and astronomers studying the universe's origins claim to have estimated its age with an impressive margin of error of less than 1%, a remarkable feat that has allowed us to determine when the universe was born. There are two primary methods used to determine the universe's age, and both are in agreement with the current estimate. The first method traces the universe's history and is an effective technique for estimating its age. This method was made possible by the discovery of the universe's expansion in the 1920s. In physics, if you understand the equations that govern a system and how it evolves over time, you can project backward or forward as long as the laws of physics and the system's composition remain unchanged. In cosmology and astrophysics, the laws governing the universe's expansion are derived from solving the theory of general relativity for a universe that is, on average, uniformly filled with matter in all directions. This is referred to as a homogeneous and isotropic universe. The outcomes of this solution are known as the Friedmann equations, named after Alexander Friedmann, who first derived them in 1922. These equations describe how a universe filled with matter must expand or contract in a specific manner. The expansion rate or contraction changes over time depending on two factors. 1. The current expansion rate at any given point. 2. The type of content that exists in the universe at that moment. Early in the field of cosmology, scientists used to joke that cosmology was about finding two important numbers. These two numbers provide all the information needed to understand the universe's evolution. The first is the Hubble constant, which measures the current expansion rate. The second is the deceleration parameter, which measures how much the rate of expansion shifts over time. What we now know is that the universe is not slowing down, as was once believed. Instead, it is actually accelerating in its expansion. If we could precisely determine the universe's expansion rate, we would gain greater comprehension of the composition of the universe, including normal matter, dark matter, radiation, neutrinos, dark energy, and other components. Additionally, we could trace the universe's history back to the Big Bang, when it was hot, dense, and contained within a small volume. A study published on July 7 in the monthly notices of the Royal Astronomical Society casts doubt on past estimates of the universe's age, suggesting they may have been wildly inaccurate. This brand new study tackles the seemingly impossible problem of the first galaxies, which has perplexed scientists for years. According to the findings, certain galaxies thought to have formed shortly after the Big Bang may, in fact, be much older than previously assumed. Observations made by the James Webb Space Telescope reveal that some galaxies, like Methuselah, exhibit a level of mass and maturity that would typically be associated with billions of years of evolution. This is a surprising discovery, especially considering that these galaxies were believed to have formed only hundreds of millions of years after the Big Bang. A professor of physics at the University of Ottawa has suggested that these unexpected findings can be explained by the possibility that the universe is much older than initially thought. His study presents a new model that extends the timeline for galaxy formation by several billion years, suggesting that the universe could be as old as 26.7 billion years, double the age currently accepted. This new model incorporates Fritz Zwicky's tired light theory, proposing that the observed redshift in light from distant galaxies is caused by a gradual loss of energy as light travels vast cosmic distances. According to this theory, light becomes tired or weaker over long stretches of space. This contrasts with the prevailing theory, which attributes redshift primarily to galaxies moving away from us due to the expansion of the universe. The tired light theory has sparked considerable controversy within the scientific community, as astronomers debate whether the loss of energy over such distances could cause not only redshift but also a decrease in the brightness and intensity of light. Critics argue that if this were true, distant objects would appear much dimmer than what is actually observed. Moreover, Zwicky's theory, first proposed in the mid-20th century, conflicted with the discovery of the cosmic microwave background radiation, an isotropic radiation present throughout the sky that represents the residual energy of the Big Bang. This radiation provided compelling evidence supporting the expanding universe theory, although Zwicky's theory initially seemed promising. Incompatible with these observations, a new perspective has been suggested, allowing the tired light theory to coexist with the universe's expansion model. According to this new interpretation, the redshift phenomenon can be understood as a hybrid effect, combining both the universe's expansion and the gradual loss of light energy during its cosmic journey. This revised interpretation not only reintroduces the tired light theory but also incorporates the idea of blocking constants as a fundamental concept. This idea was proposed by physicist Paul Dürr. These constants are physical, particle-specific parameters that govern interactions, and the theory posits that they may have changed over time. By considering the evolution of these blocking constants, the proposed new model extends the duration of the formation of the first galaxies observed by the James Webb Space Telescope. Instead of forming just a few 100 million years after the Big Bang, these galaxies could have formed over several billion years, providing a much more plausible explanation for their size and mass. This model also challenges the conventional interpretation of the cosmological constant, which is believed to account for the dark energy responsible for the universe's accelerating expansion. Instead, the model suggests a modified version of the constant that takes into account the possible evolution of blocking constants over time. This modification in the cosmological model could offer solutions to the puzzle of the small size of galaxies observed in the early universe, ultimately providing a clearer and more accurate depiction of cosmic evolution. What do you think? Have we been mistaken all this time? Share your thoughts in the comments section. If you enjoyed the video, remember to hit the like button and subscribe to the channel so you don't miss out on future content like this. Thank you for watching, and I'll see you in the next one. The study's findings are not only groundbreaking but also present a paradigm shift in the way we think about the early universe and its evolution. If this new model holds true, it could rewrite our understanding of everything from galaxy formation to the very structure of spacetime itself. A change of this magnitude has the potential to challenge the assumptions we've made for decades about the universe. Scientists have long known that the formation of the first galaxies occurred relatively soon after the Big Bang, within the next few 100 million years. However, new evidence from the James Webb Space Telescope is forcing us to reconsider this timeline. The possibility that galaxies like Methuselah could have formed much earlier suggests that we may need to reevaluate the very nature of the universe. Could the Big Bang itself be older than we thought? If so, how would this impact our understanding of other cosmic events, such as star and black hole formation? At the heart of this debate is the challenge of reconciling the various theories that attempt to explain the age of the universe. The established theory, which posits an age of around 13.8 billion years, is supported by a wealth of evidence, including the cosmic microwave background radiation and the observed redshift of distant galaxies. Most of these observations have led scientists to accept the current model, but the new study forces us to confront the possibility that this model may be incomplete. One of the most intriguing aspects of this new research is the role of the tired light theory in explaining the phenomenon of redshift. The redshift observed in distant galaxies may be due not only to the expansion of the universe but also to the gradual loss of energy as light travels vast distances. If true, this could offer a new perspective on how we understand light and energy in the cosmos. While controversial, this theory opens the door to new possibilities in cosmology that could have profound implications for how we study distant objects in space. The proposed modifications to the cosmological constant are also worth noting. By suggesting that the constant may evolve over time, the new model challenges the long-held belief that dark energy remains constant throughout the history of the universe. This idea could lead to a deeper understanding of dark energy and its role in the universe's accelerating expansion. It also has the potential to provide solutions to some of the lingering mysteries surrounding galaxy formation, particularly the small sizes observed in early galaxies. As the scientific community continues to digest these findings, it's clear that we are on the cusp of a major shift in our understanding of the cosmos. Whether or not this new model will be widely accepted remains to be seen, but it's a reminder of the ever-evolving nature of science. Our understanding of the universe is constantly being refined as new data emerges, and this is a perfect example of how research can challenge established concepts and make room for new avenues of exploration. As we continue to study the universe, one thing is certain: the quest to understand its age and origins will continue to captivate and inspire scientists for generations. Whether the universe is 13.8 billion years old or twice that, the mystery of its formation and evolution remains one of the most profound questions in science. The findings from the James Webb Space Telescope have only scratched the surface. As more data becomes available, we may uncover even more startling revelations about the true age of the universe and the forces that shaped it. So, where do we go from here? With new technology and instruments like the James Webb Space Telescope, we are now able to explore deeper into space than ever before. These advancements will allow us to gather more precise data and improve our models of the universe's history. The questions surrounding the universe's age, its early days, and the formation of galaxies are far from settled. But with each new discovery, we come closer to unraveling the mysteries of the cosmos. As we await further research and insights, it's important to remember that science is a process of continuous learning. Our current understanding is based on the best available evidence, but it's always subject to change as we uncover more information. The possibility that the universe may be much older than previously considered is an exciting prospect, one that could change the way we view our place in the cosmos. So, stay tuned as we continue to explore these questions and more. The universe is vast, and we've only just begun to scratch the surface. Who knows what exciting discoveries lie ahead? As always, we'll be here to keep you updated with the latest developments in the world of cosmology. Until then, keep wondering and stay curious.